In this video, we're going to talk about the stress tensor invariants, deviatoric stresses, the deviatoric stress tensor invariants, and relation of the second invariant of deviatoric stress tensor J2 to the von Mises stress. Now, immediately preceding this, I usually derive the stress tensor, and at the time I'm making this video for uploading to YouTube, I have not done that yet, but I will fill that in. I will be teaching theory of elasticity soon, and we do the same sort of things in that class, so I'll try to fill that in at that point. But for now, we're going to take the perspective that we have already derived the stress tensor and that we have some understanding of the stress tensor invariance and what that means. But I'm going to go ahead and write it down here. So if we want to find the invariance of the stress tensor, let's just write our stress tensor here. And I'm going to assume a fully populated stress tensor, and that it is symmetric if we have conservation of angular momentum. I could call 1, 3, and I can call this one 2, 3, and here's sigma 3, 3. Okay, so there's our stress tensor sitting here. And in general, if we solve the eigenvalue problem such that we have, let's see, sigma n is equal to, some people call it lambda, or I'm going to call it sigma pi times n. Then if we solve this, then that's the eigenvalue problem to find the principal stresses. Eigenvalues are the diagonalized form of the stress tensor. If we can find a certain set of coordinates where all we have are normal stresses, then those normal stresses are the eigenvalues. Now, to generate the characteristic equation from this eigenvalue problem, if we take the stress tensor on this left-hand side, we bring this term over to the left-hand side, and in order to have this in the right form, these scalar values, sigma pi, multiplying that by the identity tensor, I can now factor out my unit vector n, and then that would be equal to the 0 vector. Okay, so these sigma pi are scalar principal stresses. Now, there's two ways to make this equation true. Again, this being the 0 vector. Either the n is equal to 0 or the stuff in the brackets is equal to 0. The n we're not allowed to make equal to 0 because that needs to be a unit vector. Okay, so what we're left with then is this term in the brackets equal to 0. And so this must be the 0 tensor. And if that is the 0 tensor, then the determinant of the 0 tensor is equal to 0. Or the determinant of sigma minus sigma pi times the identity tensor is equal to 0. Now this is a scalar. In developing this, expanding this out, basically we're going to take the determinant of a matrix in which we have subtracted off these terms only along the diagonal elements. And in developing that, we can come up with what's called the characteristic equation. It's going to be a cubic equation, and I'm going to write it in a particular way. We're going to talk about it. I'm going to write it as minus sigma p cubed plus I1 sigma p squared plus I2 sigma p plus I3 equal to 0. And again, hopefully this looks pretty familiar. Now I1, I2, and I3 are the invariants of the stress tensor. If you read an older book like Hill's book, he uses the symbol J, which is kind of confusing because we're going to use the symbol J later for something different but related. Now the other thing we have to watch out for is, notice how I've written this. I've written this with plus signs on all the terms. So I have a plus sign here, a plus sign here, a plus sign here. Some books will alternate the signs in front of those terms. Okay, so just be a little bit careful. The way I'm writing it here is just the way that I've written it up, and it may be a little bit different. Now what we mean by invariants are that these things are not subject to change when we rotate our axes. Okay, so that's one of the defining characteristics of tensors. We can have a change of axes, and there are certain things that don't change. These are the invariants. Now if you're listening to this for plasticity, then you probably already have a good understanding of the stress tensor, so I'm not going to go into detail at this point. Like I said, I'll try to backfill later with some more details about why this is so. Alright, but these three invariants we can list, and I'm going to go ahead and write them down. I1 is the trace of the stress tensor, and what I mean by the trace is if we add up all the diagonal elements in our index notation, we can just express that as sigma kk with our implied summation. Of course, this is equal to 1, 1 plus 2, 2 plus 3, 3. Our I2 is our second invariant of the regular stress tensor, and be expressed in this manner with a double summation of I and j of sigma ij minus sigma ii sigma kk. So again, we have a double summation term right here. And then the third one, well, that's simply the determinant of the stress tensor. Okay, so we have those three invariants. All right, now we need to talk about something called the deviatoric stress tensor. We'll first define it, and then we'll talk about why we might be interested in that. And in fact, in our multi-axial cyclic plasticity algorithm that we're going to develop, using the deviatoric stresses are really key in establishing that model and getting something to work well. We don't have to use deviatoric stresses necessarily, but we'll see why they're very convenient. Alright, so deviatoric stresses are defined as the regular stress tensor minus what we call the hydrostatic stress. There's different ways to write this. So Sij is equal to sigma ij minus 1/3 sigma kk Kronecker delta ij. Okay, this is our Kronecker delta. It's equal to 1 only if I and j indices are equal. It's equal to 0 otherwise. And here's sigma kk, which we know is the trace. That's sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3 that we have divided by 3 right here. Without the index notation, the way I would write this would be S is equal to sigma minus the hydrostatic stress P times the identity tensor, where P, go ahead and write that down, hydrostatic stress is 1/3 of, depending on how you want to write this, you can write sigma x plus sigma y plus sigma z. It's equal to the average normal stress in the material. Now, hydro has you thinking something about water. Well, in fact, in a ideal fluid, If you are inside of that and have a certain fluid pressure, then the state of stress is hydrostatic. In a hydrostatic state of stress, what that means is that all the normal stresses are equal to the same value. If we were to take a cube of that material, the hydrostatic stress, either tension or compression. If we're thinking of fluids, usually we think of compression. But they're all the same value, and they're all pointed into the material, and there's no shear stress. Now the interesting thing about a hydrostatic state of stress is that if you try to rotate this cube to any direction, you still have those same states of stress. You don't ever get any shearing stress when you have a hydrostatic state of stress. Some people call this a spherical state of stress, because any which way you turn this cube, you get the same state of stress. Well, why that is important, and we'll show some evidence of this at a later point, but why this is important is that a lot of metals have been determined to be insensitive to hydrostatic stress as far as their yielding behavior goes. Okay, so these experiments go back to the 20s and 30s. Mises himself did some, Taylor and Quinney did some experiments. They're outlined in Hill's book, Theory of Plasticity. And it's generally accepted then that this is the case. Now, while many metals are insensitive to hydrostatic stress, not all materials are insensitive to hydrostatic stress as far as yielding goes. So if you have some materials like geomaterials in particular, they maybe have some porosity, they can absorb water, they can do things. You can have hydrostatic stress sensitive materials in that case. So you have to be very careful when you choose your plasticity theory that you're going to use for a particular material. Make sure you have some basis or some knowledge of choosing the right theory to go with that material. We're going to talk mainly about metals in this particular course, so that's what I'm going to emphasize here. I don't have my book with me today to be able to show you the page out of it, but there are some very nice experiments that have been done by Taylor and Quinney that illustrate this relative insensitivity to hydrostatic stress on the yielding behavior. So the advantage then of using the deviatoric stress tensor is that what we're doing is we're subtracting off the hydrostatic stress term from our stress state. If a material is insensitive to hydrostatic stress, we really don't need to worry about it as far as our yield criterion goes. Okay, and this is where we're going to get into talking about J2. Now, just like the regular stress tensor, the deviatoric stress tensor has invariants as well. Characteristic equation we can build up the same way. And instead of writing this in terms of sigma, I'm going to write this in terms of S. So S is some scalar invariant of the deviatoric stress tensor. So we have a minus S cubed. And now I've already used I, so I'm going to use J. And now, again, if you're reading Hill's book, be a little careful. He uses J prime. But J is the more standard notation these days. And I is the more standard notation for the regular stress tensor. Now our stress tensor is guaranteed to be real, symmetric, and positive definite. So we will have three values for the principal stresses. They may not be unique, but we'll have three values that are real values. The deviatoric stress tensor is the same way. We're going to end up with three values for the eigenvalues of the deviatoric stress tensors. That's what the S is. Okay, so take care with the notation. When I put a ij or a squiggle underneath it, that's the tensor. When I don't have anything underneath it, that's a scalar. So we can define J1, J2, and J3 in the same way that we defined I1, I2, and I3 for the stress tensor. Alright, so let's write those down, and we can write them down in the same way. J1 is the trace, and these things, for any second order tensor, you have the J, the first invariant being the trace of the tensor, and in this case it's SKK. J2, the second variant of any tensor, is 1/2 Sij minus Sii Skk, if we want to write it that way. And J3 is going to be the determinant of the tensor. Now let's take a look at the first invariant, the J1. Remember how we defined Sij? We said it was sigma ij minus 1/3 sigma kk Kronecker delta ij. So if I want the trace, if I want to add the three components together, basically what I'm going to have, let's see, let me be careful here. I've already used k in there. I don't want to cause too much confusion. Let's say MM. Okay, SMM is the same as SKK because we're using our implied summation notation. This would be sigma MM minus 1/3 sigma kk Kronecker delta MM. Okay, this is when I is equal to j, and they're both equal to this new subscript m from this previous equation. And let's see if we can simplify this just a little bit. Kronecker delta MM is Kronecker delta 1,1 plus 2,2 plus 3,3. By definition of the Kronecker delta, this is equal to 3. So we have 3 divided by 3. And SMM then is just equal to 0. Okay, so this is something that's very important now. We've just shown that the deviatoric stress tensor's first invariant is equal to 0. That means we can also, let me put that in a different color, it means we can also simplify our second invariant as well. Because SKK and SAI are also equal to 0, we can write the second invariant as 1/2 Sij. And we're just going to leave the last one alone. I'll go ahead and write it again just so I have it over on the side. But the third invariant is still the determinant of that deviatoric stress tensor. Now it turns out that J2 is related to the von Mises yield stress. If you're familiar with the von Mises yield stress, it has to do with the distortion energy in the material, distortion energy density quantity. And basically in class like undergraduate mechanics of materials, I talk about it. I don't go through all the details of the derivation, but I do have another video on von Mises as far as yield criteria goes that may give a little background for that. But again, if you're watching this, you probably have some experience with the von Mises equation already. Well, let's take a look at Sij divided by 2 in a little bit more detail. Alright, so in terms of the deviatoric stresses, we have a double summation, and I probably won't do this a lot, but I think it's worthwhile to do this once or twice. If we expand that, we end up with 9 terms. With our subscripts, basically we have each one of the deviatoric stresses squared added together, and then quantity divided by 2. Let's see. I will say, as I write down a lot of these subscripts, it's easy to get one wrong here or there. If you find it, make a post, and I will make a note of it. Just kind of keep me honest here. So now we have these 9 terms, and if you noticed, I've written this in terms of a non-symmetric form, and there's a reason for that. Later on, we're going to start taking partial derivatives of this, and I want to keep that separate. Okay, so partial derivative of sigma 2(1) squared and partial derivative of s(1,2) squared and partial derivative of s(2,1) squared, they're going to give me separate contributions, and I want to keep track of those separately, and we'll see why later. But for now, I'm going to write this as if it is non-symmetric, even though in most of our applications it will be a symmetric tensor. Okay, we're going to get back to this form in just a few minutes too. We'll talk about something called a yield surface. But let's express this in regular stresses as well. So we know our definition of deviatoric stresses. And we have an expression here. I've used KK already. Let me use something different. Maybe sigma MM. And here we have our Kronecker delta IJ. So let's expand this in terms of regular stress components and see what this is equal to. So I have a half out in front of this whole mess, and I'm just going to algebraically manipulate these terms now. So one of the great advantages of using index notation, so we can do algebraic manipulations on complicated matrices effectively, tensors. And on my last term I have a ninth, sigma KK, sigma MM, and then I got a Kronecker delta IJ, Kronecker delta IJ. Alright, now we know from our index notation discussion that Kronecker delta can act as a replacement operator on indices. So for example, Kronecker delta IJ times sigma IJ, I can represent that as sigma II. And here again, I could represent that as a sigma II or sigma JJ, same thing. And again, acting as a replacement operator, I have sigma Kronecker delta II. And Kronecker delta II, we know, is equal to 3. Let's go ahead and rewrite this one more time. So we have 3 over 9. That gives us a third. And if we look at this, this last term and either one of these two middle terms will annihilate each other. And the last term that I just wrote down is the trace of the stress tensor squared. I'm going to do a little bit more algebraic manipulation here. I'm going to pause the video and just write down a couple of lines. First, by expanding out the sigma ij term, and then by multiplying out the square term of those three normal stress components. And then by simplifying, by subtracting off some of those terms that I can. And at this point, also invoking the symmetry of the stress tensor. So sigma 1, 2 is equal to sigma 2, 1. Okay, I'm going to do a little bit more manipulation on this. I'm going to factor out a 1/3 from all the terms. And we start to see a pattern that is going to begin to look familiar. We have 6 times the shearing stress terms squared. And if we look at the top line, this line right here, you can see my cursor, we can regroup those terms as a set of differences squared. Right, and in doing so, we get this following expression, and you may notice that the term in the red brackets that I have here is the von Mises stress squared. So I'm going to write down it's equal to 1/3 sigma von Mises squared. Alright, so J2 then is 1/3 sigma von Mises squared, where our von Mises stress is our usual definition. I'll go ahead and write it down. 1 over the square root of 2. If we want to do it in terms of x, y, z coordinates, sigma x minus sigma y, quantity squared, sigma y minus sigma z, quantity squared, sigma z minus sigma x, quantity squared, plus 6 times each of the shearing stresses squared, all added together with the square root and then divided by the square root of 2. At initial yielding, one half Sij is equal to 1/3 of sigma naught squared. Okay, so sigma naught is the initial yield stress. Or if I want to manipulate this just a little bit more, I can say that Sij is equal to 2/3 of sigma naught quantity squared. Okay, so now it's not J2 anymore, but it's within a factor of J2. So Sij is equal to 2/3 sigma naught squared. Okay, now at this point, I want to show you something that I think is kind of interesting and forms the basis of yield surface plasticity. And that is when we expand out the left-hand side of that expression, we have an interesting form in terms of deviatoric stresses. And expanding that form out, we have our 9 terms over here, S11 squared plus S12 squared and so forth. It's equal to 2/3 sigma naught squared. Well, if we think of this in just the right way, this really looks very similar to the equation of a circle. And the equation of a circle is like x squared plus y squared is equal to some radius squared. Of course, the equation of a sphere is x squared plus y squared plus z squared is equal to r squared. But what we have here are 9 quantities squared is equal to some r squared term. What we have here is the equation of a hypersphere. and it's a hypersphere in 9 dimensions. And that's very interesting. I think it's geometrically very satisfying, I guess. Now, obviously I can't draw a 9-dimensional hypersphere on the page, but I can draw one plane of it, and that one plane will look like a circle. So pick any two axes that you want, S11 and S12 or anything. And in general, when I represent a yield surface, I will just kind of draw a circular shape. There are certain constraints on the shape of this circle. We'll talk about those soon as well. But this is a circle. It's a surface, and that surface has a radius. Call that capital R, and our capital R is going to be square root of 2/3 times sigma naught. So it's a hypersphere of this radius. Now, what makes this very nice for us to deal with is that we can show that we can use this surface as a plastic potential, and normal vectors to this surface are related to the directions of our plastic strain increments. And we can do lots of other interesting things. And we've reduced this very complicated problem to basically a solid geometry problem. Alright, so we'll get into that more as I continue these videos.